Now we're going to change up what we're doing. Before we've been talking about functions of a single variable and solving equations with a single variable. What we're going to do now is look into more than one equation, more than one variable. So here's our first example. And all I want you really to get out of this is the outcomes, what can happen. That basically there's a result at the very end, but I want to illustrate where it comes from. So I have these examples. Okay, system means there's more than one equation, right? In this case, two. So system of equations, system means more than one. Linear means that notice all the variables appear only to the power 1. Only to the power 1. So you have x or y. You can't have x squared. You can't have xy. You can't have sine. You can't have e to the x. You can't have log. You can only have x to the power 1, y to the power 1. That's all you can have. And then they're equations because of the equal signs. Now, we're looking at two variables here, but you can have more than two variables. Okay, what we're going to do in the next section is 3 variables, and what we're going to learn is how to solve these methodically for really any finite number of variables, okay? But for the moment, we're just going to have 2 variables, x and y. Okay, that's fine. Okay, so we're ready to go. System of linear equations. Now again, we're going to have more equations and more variables, but the basic holds up, so let's just look at this. How do you solve this? I'm just going to bring them down here. And all I'm going to do is I'm going to solve one equation for one variable. Doesn't really matter which one. And I'm going to plug that into the second equation. Plug it into the second equation here. And I'm just going to solve all this. Now I notice I only have one variable, x. I'm just going to solve for x. I'm going to drop the brackets here. Combine the x's, combine the constants. Put the constants over there, so x equals 2. Okay, so I got x equals 2. And now I'm going to come back over here to one of my equations and get, well, y is minus 3. So I have x is 2, y is minus 3. Can I check? This is a key idea. We're going to check. I'm going to plug them into these equations and see if I get the correct answer. So I'll plug in the x and y values in for x and y, and they better check out, right? They have to equal each other or I made a mistake, and they do in this case. 5 equals 5 and 1 equals 1. Now I'm just drawing the graph because even though we go to more variables, this same scenario holds true. Notice, for this equation, that's a line, that's this one. And it's the red line. For this equation, that's the line, right? Intercept 1, slope minus 2. So intercept 1, slope minus 2, and you get this line. Notice what I have. I have one xy pair that's in a solution set of both equations. Right? So notice, everything on the blue line satisfies the one. Everything on the red line satisfies the other equation. This particular point, and only this particular point, satisfies both at the same time. Right? It lies on the red one, so it's in the solution set of the red one. Right? The graph is the solution set for the red one. Right? And it's also in the solution set of the blue one, right? That's what the graph is, a set of all xy pairs that make the blue equation true. Okay, so that's what I have here. So that's what I have here. And that's my xy pair that's satisfies both. It's in the solution set of both. Okay? So check. So notice I have one and only one solution that makes both of those equations true at the same time. Now let's look at a different one. Okay, I'm just going to bring them down. And again, I'm just going to do the same. I don't need to get fancy. I'm just going to solve for one of the variables. I'll plug it into the other equation. Right? I'm just going to clean it all up. I'll distribute the 2. Put the y's together. Look what happened here. Minus 2 equals 5? Yeah, you should be horrified. That's an algebra state. No. What happened? Well, it's not true. It means there's no solution. The premise of doing algebra is that when you begin, there is a solution. So when we get minus 2 equals 5, it's a contradiction. Minus 2 can't be equal 5, so there is no solution. That's what that tells you. Keep that in mind. When we have a contradiction, it contradicts the fact that we said there's a solution, so there's no solution. This is going to come up again in the next section, and that's why I want you to remember. Now what happened here? Notice the first is this equation. The second is this equation. Notice they have exactly the same slopes. So they're parallel. They have different y-intercepts. So that's why we have no solution. There is no point that lies on no point that you can find that lies in the solution set of both of those equations. So again, we had a case where they intersected one and only one solution. We had a case where there's no solution. Absolutely not. And let's look at this case. So here's a new system of equations. Okay, let's just solve it. Bring them down. I'm just going to do elimination this time. Other one was substitution. I'm just going to multiply the first equation by 2 and add it to the second. So I multiply the first equation by 2. I'll add them together. And look what I get. 0 equals 0. Now what is this telling us? This isn't a contradiction. This isn't a contradiction, so let's see where this came from. Notice they're both equations. You can solve them. They're linear. You can solve them for the equation of a line. Notice they have the same slopes, so they're parallel. But notice they also have the same intercept. They're exactly the same. They're the same lines. So they have the same solutions. Infinitely many solutions. So 0 equals 0 tells you that you don't actually have 2 equations, you only have 1. We have infinitely many solutions, and here's the picture. Notice the 2 lines are exactly the same. That's why I'm getting kind of a purple color there. It's a red line and a blue line on top of each other. So that says that I have infinitely many solutions. So let's summarize this, because this is going to play out in the next section. For a linear system of n equations, say 2 equations and 2 unknowns, 3 equations and 3 unknown variables, 4 equations, 1 billion, 1 trillion equations, and 1 trillion unknown variables, there's only 3 possibilities. That's it. You cannot have anything else occur. If they're linear, you could have one and only one solution, not 2. If you're going to have 2, you do one and only one. If you have 2, you have infinitely. And there's my picture. No solutions, that case, or infinitely many. Those are your only possibilities. So if you found 2, you have infinitely many. One and only one, no solution, and infinitely many. And this is true for any linear system, 1 billion equations and 1 billion unknowns. And in the next section, what we're going to do, we're going to learn a methodical way of finding those solutions. We're going to follow an algorithm. So I don't have anything specific here that you need to be aware of. You should be aware that there's 3 possibilities. One and only one solution, no solution, or infinitely many solutions. That's what I want you to retain. Okay, well, not a bad lecture. Okay, good luck.